don't know how to, like, do you see all the people pictures, or do you just see my screen now?
I can see your screen, yeah. I can see the slide.
Okay, so you don't see like me and you and everybody else, because...
No.
Okay, awesome. I don't have like, usually I don't use a single screen. So, hi guys, once more. I sincerely apologize for being late. So I will skip the introductions just so we can go to the content. And of course, I hope to have a nice Q&A session. Most likely you don't know me. So my name's Lukasz. And as you learn, I have 4 kids and a really difficult situation right now. But I also have a PhD in shell stability. I have a design that does FEA. So I kind of know what I'm talking about, at least I hope so. And also, I've been a lecturer for 10 years and I run a blog. So running a blog is like the most important credential, clearly. And today I want to talk to you about how to reasonably do nonlinear FEA. And let's start with this. Usually when people, because I'm a structural engineer, and I think that we should start here. And that means that what I use FEA for is design. And that's not obvious in any, like, that's not obvious at all, because FEA can be used in various things. So I will here talk about structural design. That is the thing that I do and I enjoy most, and this is what I'm qualified for. So if I would have to say one biggest issue people have in FEA in general, because I do training, I coach people in FEA, and I do consulting things, it would be stress is higher than yield. So today I've selected a subject that is the 90-meter chimney. It's an actual structure, although I haven't designed it. I was just asked to verify a few things after this was built. One of the biggest questions people usually have would be stress is higher than yield. And let's start with this. You can see that this would be a linear outcome of the stress analysis. And I don't want to go deep into what the load should be applied and so on and so forth, because that's, at some level, especially in structural design, that's a very small problem, because it's not a big issue in itself. This is codified. You can check the values in codes and things will be fine. But when people struggle would be, okay, so I did a linear FEA, I've got this outcome, and now we have to say, is it good? Is it not good? What to do about it? And of course, since this is a nonlinear FEA lecture, you would expect me to show something like this. You will notice that the stress scale changed, and that the maximum on the right is 224. If you do structural steel, you will notice that it's a funny number. That's because of temperature. It was like the fumes that go through the chimney were hotter. This reduced yield strength of a steel somewhat, but it's irrelevant to the discussion today. But actually, that would be cheating, because it's the same outcome. I just changed the color scale. And I'm changing the color scale here mostly to force you, in some sense, to think about something. And that is, assuming that the yield is 224, as you can see here, so we are like what, 3, almost 4 times above yield, right? Would you say that this survives based on the outcome you see on the screen? And I mean, like, I already told you that it was built, so kind of like you already know that it would survive, right? But at the same time, you can think, how big stress value from linear FEA would you be willing to accept before you would say, it's too much, right? I have to say, no, we have to do something, right? And that would be the problem that we'll try to tackle today, in some sense, at least at the beginning. What the stress you would accept, you can write down a number. You don't have to, we don't have to vote on this either, but it's good to have a number in your head as a mental exercise. We'll get to this in a second. Effectively, what I hope you will notice is that the design based on linear FEA would be something like, let's do a linear FEA. We will obtain a stress value. This stress value will be higher than yield, obviously. And then we will have to essentially guess, are we willing to accept this value or not? Like, if you would like to check a structural code of some sort to see how much bigger stress than yield are allowed in design, you would be greatly disappointed. Unless you're doing like super old-fashioned pressure vessels according to Adam Erkblad or linear ASME. There wouldn't be any rules like that, because if you think about them, those would be like pretty bizarre, right? And yet you have to do the design somehow, and that's the truth. So before we move any further, I think that I should really briefly explain to you how FEA works. And I know that Józef organized this very neatly, and I'm pretty certain we already had some discussions about FEA, but I have a relatively weird approach to it. So maybe what I will say here will help you in a bit. So imagine that we have a single FEA element. And then you already most likely know how the FEA, the simple linear FEA equation looks like. That's like pretty not important really, and that's the only equation you will see today, so don't panic on me. What's important is that essentially what FEA does, it calculates displacements of the nodes, and thanks to the fact that we already know how the displacements look like, we can calculate, this is of course done based on stresses, and if you calculate the deformation of the nodes, sorry, I'm trying to speak faster than I think, you will get strains. And based on those strains, since you have a linear material law, you will be able to calculate stresses. So effectively, we had four things. Firstly, we applied loads. And then, thanks to the loads that we applied as a user, you can click solver doing calculations. Firstly, it calculated deformations. Based on the deformations of each element got strains, and then based on those strains, element got stresses. So effectively, you could use something that would be called work principle. You can calculate the external work, that would be the work of applied loads on the deformation of the model, and internal work, so work of strains on stresses or on strains. And those two, thanks to the work principle, should be equal. And what is important is that this value combines the input and the output. Note that the applied load is something you insert, while deformation strains and stresses are something that you calculate for. So you can say, okay, my input is tied with some portion of the output, and this should be equal to some other form of. So,
Lukasz, one thing, I think your microphone completely gave up. We can't hear you. I thought it was me, my cheap headphones, but it's actually you. Basically for like 30, 40 seconds, I can't hear you, Lukasz. Something happened.
do you hear me now?
Yeah, now it works.
Well, if you wonder why I have like secondary blue earplugs in my backpack.
Okay, folks. I think it was for 30 or 40 seconds. If you could repeat what you said, that would be awesome.
So maybe I will start with this.
Let's go.
So how FEA works is you have a finite element. Firstly, you calculate the deformations of the node in the element based on the loads you apply. And of course, there's like a equation, governs this that we all know. And then based on those deformations, you calculate strains. Based on those strains, thanks to the fact that you define the material, be it linear or not, like let's leave it for now. Based on the strains, you get the stresses. So thanks to the ERC principle. I'm trying to translate things in my head into English as I speak. That looks funny. You have something like this, that there is a work of applied loads, something you as a user defined, on deformations. And then this work would be external work. And external work has to be equal to internal work, so work of stresses on strains. And otherwise, your model wouldn't be in equilibrium, essentially speaking. And this ties together input and output. So you can actually check if the solver did something stupid or not. That would be called convergence. So let's assume that like you have a solver that doesn't function really. You do some random calculations, and suddenly you check, oh, I can check external, internal work. There are not equal, something went wrong, right? Of course, in linear FEA, you instantly assume that it will be correct, but this will be useful later on. And so knowing this, let's wonder for a second why we get those funky super high stresses in the model. And while it was like 3.5, almost 4 times higher than yield, why it didn't fail? So firstly, how do we get yield stress? Like you can take a simple tensile test. And while the chart actually shows you the relation between force and elongation of the sample, we could easily transfer it to make it stresses and strains simply by dividing by length, dividing by cross-section area, and so forth. So you will notice that, okay, I have a yield strength here that's 235 in normal temperature, right? So you could think, yeah, but then, somewhere after the plastic plateau, the curve increases, the material strengthens. So clearly that's the trick, right? This is where the extra strength is in my material. Actually, it's not. It's in plastic plateau. So firstly, the stress on the top there would be like 360 according to Eurocode. So it's still like at least 2 times too little to solve the mystery of why this haven't failed. And the plastic plateau is something which is very often not understood. And I want to explain this to you as we move on. And I remember that the professor that taught me steel structures divided the curve always to 3 parts. The linear part is for beginners, then the plastic plateau is for the experts, and the strengthening afterwards is for people who are desperate. Because usually very little lies in this portion of the curve. So it's like a very funny joke, at least to me. So now let's look at this from the perspective I love the most, guys trying to carry a rock. When you see there on the stiffener, I wonder if I can make like some sort of laser here. Here, like I will be talking about this zone. When you see it, there is like a small red zone. Of course, a lot of load is going through the stiffener, and the stiffener ends very quickly, drastically in one single point. That would be the red guy in this picture on the right. Imagine that the load going through the stiffener is like a huge stone. And this single guy tries to essentially carry all this weight by himself. And in linear realm, that's really simple. You define the relation between stress and strain, the Young modulus, right? And if you have like significant strain, you will get significant stress. That's very simple. But also under this load, there will be some deformation, right? And these deformations mean that our red guy kind of like goes a bit down, asking the green guys to help him, right? But truth be told, in a linear regime, if you would calculate that, the formation for 870 megapascals of stress would be very, very small. So while a small portion of the model would help, because it wasn't like one red point and nothing else, right? There was like a small bubble of stress. The reality is that it wasn't super high. So this is how you see the outcome, right? There's like a red dot, a bit of green, a bit of blue, and then nothing, right? So the outcome from linear FEA is we have too much stress, right? So how this works in reality is that initially the red guy responds in a linear way until you reach yield. And then note that nonlinear response in this case means that after reaching yield stress, the guy can kneel, so the strains, the deformation is free, while he still transfers as much load as he was before the plasticity happened, right? So the stress do not decrease, but it doesn't increase either. It's constant, but deformation increases. And as this happens, you will notice that the green guys can help, not because the red guy carries way more, but he just kneeled, he deformed, allowing other people to help out. And then, of course, as the green guys kneel as well, the blue guys can help as well. And so the model deforms, and deforms. And more and more people, we have a problem. More and more people are trying to help out transferring the load. And this is why this hasn't failed. Because while, okay, we have a huge stress, realistically, it will be distributed on a bigger area. And so we can say, okay, remaining stress will simply go to the next guy, right? So we have a yield stress of some value, and then the rest simply is like spreading the butter on the bread. It just goes to the sides. And this is realistically, Martusiu, pójdziesz się pobawić ładnie? And realistically, this is how the stress distribution looks like, right? You can see that the zone is a bit bigger, but not a lot. The stress is constant. It was just pushed away. So what I really like to show people is this model I've made from one of my customers for a training, because this is the highest stress peak I've produced in linear FEA. With 5,500 megapascals, this structure, when you do nonlinear FEA, was absolutely fine. So it was like 20 odd something times the yield. So it's no joke, right? And of course, when you calculate it with plasticity, the stress will just redistribute to other regions, and it works, right? So this is effectively what we are dealing here with. Of course, I can show you that comparison on the left, you have linear outcomes, on the right, you have nonlinear outcomes. But notice that the distribution of stress, while similar, is not exactly the same. Why? Because the picture on the left here is just linear outcome with like cutoff scale on the color scale, I manual input as a user. And of course, when material yields, it pushes the stress out. So the yield zone will always be higher and potentially in a different shape than what you would estimate based on linear FEA. That is because the model will push the stress according to the rigidity of the model. So it's not randomly, it's not like, 20 centimeters in every direction or something like that. It happens as the model deforms. So this doesn't have to be linear, and actually rarely is linear. Right? So when you, like the common, and this is what scares me mostly from the lectures that I do, that the common conception would be, oh yeah, Lukasz just told us that we can ignore peak stresses, right? Like, think about it. I just showed you that there was like a model with 5,500 megapascals and it was okay. So the clearest, easiest conclusion would be, awesome, let's just ignore peak stress from linear analysis. We all know, as Lukasz said, that it will yield and redistribute and whatever, that would be fine, right? But I explained to you how convergence works purely so I can use this argument. Note that when we were discussing how the model behaves, if we wanted to check if it's in equilibrium, we took applied loads and deformations, calculated external work, and we took internal work and checked it, and they had to be in equilibrium. And now, after the solver solved your model, you want to ignore stresses. So that would put your model not in equilibrium, and it's risky. Możesz dwa. So that would be the problem. And real outcome from nonlinear FEA like this, and clearly you can see that on the left the loads are lower, on the right the loads are increasing.
Lukasz, I think you again have mic issues. Only 10 seconds, I think. Is it also for the rest? Maybe put it in the chat. Yeah, okay. It's for everyone. I think you turned your head and then suddenly your mic broke.
I don't know if you hear me right now. Do you hear me now?
Yes, now I hear you.
Okay, so I'm actually running out of like headsets that would work, but it has to be something else, because like, what's the chance that randomly 2 sets of headsets would get like? Just let me know when they will stop hearing me, okay? And
Yeah,
sorry, normally I have like a way better mic at the office, but
that should work. Maybe once you started switching the slides, I think that's when it happened. So maybe 10 seconds.
So what you see here is the actual outcome from nonlinear FEA. And you can clearly see that from the left, the load is low, to the right, the load is high, right? And this is where most people using FEA stop. And my question is, okay, so when it failed, right? I mean, on the left, the load is low. On the right, the load is high. You have some in-between outcomes. So when the failure happened. And the funky thing is that you don't know based on this. And that's where people usually tend to say, oh, linear FEA is stupid, let's do nonlinear FEA. They do like whatever. They get a nice picture and say, see, it works. But realistically speaking, there has to be some sort of limit that would mean, okay, this is okay or not okay, right? So the reasonable question would be, are things immortal? Because, you know, I can always increase the load. There is always one more guy who will kneel a bit, and a bit more model will take a bit more stress. And until I yield like literally the last finite element in my model, things should be okay, right? And how to deal with this? Like, firstly, this is a model I really like. This is what you can get in a nonlinear FEA. If you use nonlinear material, notice that like if I would have sufficient enough of computing time, I could literally yield the entire model. You can even see how the neutral axis in bending is forming in like a straight line. This is where the bending doesn't happen because it's a pure bending case, right? So you could really, in nonlinear FEA, push your model to yield it completely. However, there is firstly, a very practical thing. You can only have so much plastic strains because at the end, the material simply ruptures, right? So I can do the calculations and say, yeah, okay, I don't want to use elongation. Like each steel has to have at least 15% of elongation before it breaks, but you know, 15 would be basically a toss of a coin, right? So realistically, we should use a smaller value of plastic strains, but engineeringly speaking, you want to have like a safety margin on it and so on and so forth. So there is a value you could derive from codes or procedures you enjoy and use in design to have the value that actually makes sense, right? So far, we've talked that the stress goes to the next guy, but I showed you that there is this desperate part, right? And I have to explain that it's not as desperate as you might think, although there is a good knowledge in it. Firstly, it comes with material models. And firstly, I thought that when you ignore this strengthening, as you see on the left, that would be like a horizontal material model. And I thought that the bilinear model had a hardening slope, so you can use it like this. That was my initial assessment of why would somebody do this. But actually, there are other materials like aluminum or stainless steel of some grades that would be way better approximated this way. But you can, of course, geek out about material models as much as you like, but it doesn't really change this much. What I want you to remember is that for structural steel, the plastic plateau length is around 1.5 to 2.5% of plastic strain. So you have this much length of plastic plateau. And if you're not sure, I would take the lower value rather than the higher for structural steel, because some of those really have like 1.5%, and 2.5, it would have to be like a very ductile grade to get it. Right? So the difference between the super advanced funky model you can find in some like scientific papers would start actually after around 2% of plastic strain. So after the strengthening started, your bilinear model starts to be not very accurate, right? But practically speaking, this extra stress I marked in green here wouldn't really contribute much to the capacity of the model. And that's something that's really good to remember. And when my professor said that the green strengthening part is for people who are desperate, it's not that it doesn't count. It's only the fact that this extra stress you can transfer wouldn't really impact the outcomes. Although having the percentage of plastic strains allowed reaching there actually helps, because this allows your red guy to kneel even more, so more and more of your model can help you out. So most of the important things happen as the guy kneels. So this happens like on the very beginning of yielding. And that is because, realistically speaking, the highest plastic strains will only happen in very small places. Like there won't be a lot of... Co jest, Markusiu? Za godzinkę, dobra? Pobaw się, proszę. The real plastic strains that would be like 5%, let's say, the value you read from your analysis, this would happen on a so small area of your model. Then it doesn't really matter if the red guy can transfer 235 megapascals or 300 megapascals. Even if he can transfer more, it's such a small area that it doesn't change the outcome, especially since we are looking at this stone in 2D. But realistically, this is like a circular stone, and the blue guys stand in a circle, and the green guys stand in a circle with one red guy in the middle. So it's way more important to increase the area by guys kneeling, so by plastic strains, rather than the strength of this one guy in the very middle. He doesn't really contribute that much because he's one guy. The green guys will help so much more than this one guy in the middle. So this is why I think that the bilinear material model for steel is actually on point, and it's just perfect, to be honest. I think that well, this is first and foremost how I do my FEA, and this is how the normal outcome from nonlinear FEA would look like animated, right? Okay, sure. I am ignoring the strengthening, so realistically speaking, someone could accuse me of saying this is not real, but I'm simplifying the model and I don't lose any accuracy whatsoever. So I'm pretty certain that it would be quite easy to defend outcomes like this, especially since if you take that into account, it would really change the outcome. And then this is the material model that I'm using, although we still haven't answered a question of, okay, but is there anything else than plastic strains, right? Because, okay, I cheated, right? I showed you the stresses. I could also show you plastic strains, right? And you can say, okay, here plastic strain is 0.3, 1.4, 0.04, 17, 36. You can say, okay, I'm willing to accept this much plastic strain. This is failure. So firstly, you see a clear criterion that was not present. It's not the stresses that would dictate the outcome, but the strains, right? But then there is one more thing, and we have to go back to the question of, are things immortal? And that is because if I would show you strains in this model I can promise you that those will be below 1%. Every code that I know of allows more plastic strains in a steel structure, like a structural steel. And you clearly see that something is wrong. I mean, like, can you really yield like everything before you say it failed? And the difference is with nonlinear geometry. Notice that the animation changed because this is the outcome of the analysis that not only has a nonlinear material, it also has a nonlinear geometry. And this changed how the model reacts to being yielded. But to discuss this, we have to kind of touch on nonlinear geometry in design and stability in some sense. I will try not to geek out about it this much because I have a PhD in stability, so I'm kind of like a weird guy to talk about it. I will try to keep it like simple and friendly. But what I like about stability, well, actually what I don't, what I find fascinating, let's say, about stability is that it attacks from shadows, right? If you do a linear FEA, and you get stresses higher than yield, you instantly know that something didn't work. Stability shows no warning, and your model can buckle under stresses way lower than yield, and it would still will be destroyed, but your linear FEA wouldn't show you that. So when I talk about stability, people instantly think about like classical Euler's column, the bifurcation, the stuff that when I press, things will run away from the load, right? That would be the classical buckling. And of course, that's true. This can happen in your model, and you kind of have to be aware of it, right? But of course, you can also have lateral torsional buckling. This is what happens when a beam in bending fails due to stability instead of stress. You can also have local buckling, which would be pretty like interesting. Like you can still use some code designs to deal with that in some very simple cases, but in the complex ones, you'll already have to do FEA to deal with that. You can have shear buckling, so buckling happening in bridge girders if they are high enough and have thin webs, or in shell structures, as you can see on the right here. This is why when you look at the steel bridge, it has stiffeners near the support. On one hand, you don't want to crush the support, but also those stiffeners prevent the shear buckling. And of course, then you have shell buckling, which is so complicated that it's like it's entirely different thing. Shells buckle really, really ugly. So the typical solution to this problem in a linear realm would be to do linear buckling. There is an analysis in your solver that's either called buckling, linear buckling, or something along those lines. And I'm absolutely certain that that you know how to use this one, right? And those would be the typical outcomes you can see from this analysis. And the problem with linear buckling is that it contains a lot of errors. So you can't use imperfections. Linear geometry is used all the time because it's a linear algorithm. You have to use linear material. And this means that linear buckling over-predicts the capacity, sometimes significantly. And by this, the problem is that, okay, let's do linear buckling. And again, just as with stresses, you have to guess. I get an eigenvalue from linear buckling. It may be 1, 2, maybe 4, right? And you have to guess, am I willing to accept it or not? And based on this guess, you are making a design. And I don't know about you, but I don't like guessing at all. So if you would look at the chimney structure that we are discussing here today, you will notice that linear buckling showed the first failure at a multiplier of 0.11. It's down in the left corner. And 0.11 means that the applied load should be multiplied by 0.11 to cause failure. So like if you would like to translate it to more like human language, the model is 9 times too weak because only 11% of the load causes failure. And you can see that, you know, the weirder the form, the higher the multiplier, although based on this outcome, you would easily guess, okay, this is going to fail, right? And yet I told you that somebody built this chimney and it was standing when I was making this analysis. So clearly this is problematic, and it's not easy to say, is this okay based on this outcome? So this is why to analyze it better, instead of using linear buckling, it's better to use nonlinear geometry, as this is way more reasonable approach. And as you can see, nonlinear geometry allows you to calculate local stability. You can calculate shear stability, the one that's very difficult to catch if you're not searching for it. Lateral torsional buckling, yes, it's doable, although like there are easier ways to design beams in bending if you're using structural design. And then, of course, you can do all kind of weird analysis that would calculate bizarre failure modes of complex structures. And that's the thing, because when buckling is easy, there is a simple equation governing it. You can fill it in, use your structural code of choice, press play, and you know the answer. You can have a spreadsheet in Excel that calculates. But when things become complicated, it's getting complicated really fast to the degree that it's actually more or less guesswork, unless you're doing a nonlinear FEA. So if I would only use nonlinear FEA, nonlinear geometry of our model, this is how the failure would look like. And you see like on the left again, it's less load and then it increases because animations sometimes are hard to follow. And so notice that the failure mode looks like this. But if we include both yielding and buckling in the same model, this is how it would look like. And you can clearly see the failure on the right. And I think I don't have to convince you that this actually look realistic as a failure mode, unless it looks realistic to me because I've spent my life analyzing structures like this. So now we have to wonder, okay, we know that we need nonlinear material and nonlinear geometry. So how to analyze the outcomes, right? Because again, you can look at this. We know that we have to measure plastic strains. That's one thing. And we clearly know that something like buckled, although like plastic strains wouldn't be very high if something buckled. You can buckle even on stresses lower than EU, right? So there has to be another metric that will tell us if our model failed or not. So to do this, you use equilibrium paths. And that's a concept that sounds very scientific, although it has incredible practical utility. Imagine that you have a beam, you load it, and as you load it, you measure the load you apply and the deformation of the model. And you can see I'm marking those on a chart. And then I can increase the load, there will be higher deformations, and so on and so forth. And if I connect the dots, I will get a curve. And you can say that this is a linear analysis because the curve is a straight line. If you wonder what is linear or nonlinear in FEA, this is the line that is linear or nonlinear, essentially. That's the one, right? So if I would use, for instance, a beam that can enter membrane state, it will strengthen. So I would have to press more and more to cause deflection, and the curve would not be a straight line anymore. And a line measuring applied load versus the deformation of the tip of the chin, in our case, looks like this. You can see the animated outcome of the model and how the chart looks. And I will just switch to the drawing one because there are a few things I want to know. Firstly, when FEA works, you apply load in certain increments. And note that, of course, the solver will assume that everything is linear because this is how it's trained to do, right? So you apply the load, it will calculate the displacement and try to see if the internal and external work is in equilibrium. But our problem is nonlinear. The solution we assumed was linear. It doesn't work, right? So it will show, you're stupid, this outcome is stupid, life has no meaning. And you basically start to cry. But the solver doesn't give up that easily. The easiest way it can do is it can reduce the load to find where the model would be in equilibrium again, right? So you find a place on the curve, that's great, although this is not the place you wanted because you apply the load increment of a certain value, and this is not this value, so it's not a solution you're searching for. So it will try again, right? Again, it will fail, but fail a bit closer to the outcome, again, again, and finally you will find the load on the equilibrium path. And those are called iterations, the tries of finding the answer, while the load you apply, the portion of the load you apply, is the increment. And of course you can say, oh, my analysis has difficulty to converge. I will use smaller load increments, or I will allow more iterations to make this work. And this is important because if you make a too big increment and you allow only a few iterations, the solver will end up in this place and throw an error message saying the analysis did not converge, have a nice day. And then you don't get your outcomes. Of course, this is not the only problem with convergence. You can also try to load your model with loads that are way higher than the capacity of the model. And then you can clearly see that it will never converge. So non-convergence must be the most hated error message of FEA. And to solve this, you would actually need an arc length method to solve this problem. And if you would use arc length method that iterates the load a bit differently, you will notice that this curve, the equilibrium path, has a clear tip. The capacity increased and then it decreased, so the model failed. And you can say, okay, if I would multiply my load by 1.35, because on the right, you don't see the load because, load on a chimney is a rather complex thing. There are a lot of forces in a lot of directions. So instead, I applied the loads and simply multiply them by small number, then bigger number, then bigger number, then bigger number. This is called load multiplier. And it actually makes sense. If I would increase my load 35%, the model would fail. So first of all, I'm good, right? The load on 1 is still okay. The model would not fail. And this is why this chimney actually stood and worked, right? But you can also notice that there is something funny happening in the equilibrium path. Notice that initially there was one curve, and somewhere around the multiplier of 0.3, something happened and that curve kind of turned. If you would be used to analyzing the nonlinear FEA outcomes, you will instantly notice that this has to be investigated. And let's wonder what happened there. Do you remember the linear buckling outcome I showed you on a multiplier of 0.11? I won't even comment on the fact that it was 3 times wrong because the actual multiplier was 0.3. It showed that something is happening to this. And if we would compare linear outcomes and nonlinear outcomes, you will notice that there is a distinctive change in this plate, and it happens around the multiplier of 0.3. You see, this plate strengthened the structure if the wind was in a correct direction, and it would actually buckle under the load multiplier of 0.3. And this can be surprising, of course, but you could actually predict it. It didn't cause the model to fail. It still functioned again, but it lost a certain portion of its rigidity. And this is what you can see here, this change in the curve with actually something secondary failing in our model. It didn't cause failure, but it changed how the model behaves. So nonlinear FEA give you a powerful tool that actually allow you to not only just analyze things and see what's going on, but also to really pinpoint weird things. And I would say that that's a good way of doing nonlinear FEA. So you can see here that this is how the stresses look like. You already know that you want to look also on plastic strains, but note that I can tell you that the failure is the third one from the left with 2.8 plastic strains. Those plastic strains would still be allowable. So plastic strain is not the only metric of failure in nonlinear FEA. It's the equilibrium path that you also have to analyze to see if perhaps there is a drop in a curve. With nonlinear geometry, this drop will almost always happen. And this means that the model simply buckles. It can buckle in elastic regime, it can buckle in plastic regime, but plastic strains alone will not mean failure of your model. Yeah, so that would be what I wanted to show you here. I will stop sharing my screen just so you can see my ugly face. And if you have any questions whatsoever, I would love to answer them. So.
Great presentation, Lukasz. Really much appreciated. We have one question in the comments. Can you see the chat, by the way?
Yeah. I think I can. Sadly, I can't read and talk at the same time. So a nonlinear analysis is done as an extension or next step to a linear analysis of a structure for a simulation where the loads are almost near the strength of the material used. Do you understand correctly? Yes, I would like this. Okay, there's a lot to unpack here, so I will try to answer it sequentially. Yes, nonlinear analysis is a next step of doing the analysis as opposed to linear analysis. That's true. And then it really helps you to analyze the model that is close to capacity of the model, because thanks to nonlinear geometry and nonlinear material, you can kind of like measure what went well, what went wrong. This makes sense. The problem is that when you would use linear analysis as a, let's call it, first step, the linear analysis can be greatly wrong about the outcome very, very quickly. If you remember, the stresses in our case were like 4 times higher than yield, maybe 3.5 times higher than yield, while the model, according to nonlinear FEA, had still a safety margin of around 35%, maybe let's say 20% because of the safety factors. So realistically, there was a huge difference between what linear outcomes would tell you the failure is and what nonlinear outcomes told you the failure is. The thing is that if you do linear analysis based on the outcomes of linear analysis, you may think that you're close to how much the structure will survive, while in fact you are very, very far away, and this structure can survive way more than only what you think it will. So why I completely agree with your statement that nonlinear analysis is great in analyzing the models that are close to capacity. The question is, how will you know based on linear outcomes if you are close to capacity or not? That would be the difficult part. And I think that it's worth knowing that linear FEA has terrible problems with, especially in complex cases, to assess what is the possible capacity of your model, because linear buckling under-predicted the load 9 times, stress analysis under-predicted the load like 3.5 times. So based on those outcomes, how would you know if the model is close to failure or not? I would say that nonlinear analysis is a next step, but more in a sense that it gives you way more powerful tools to increase accuracy of your calculations. So it's not whether I am close or not close to the capacity of the model, but rather how accurately I can assess what is the capacity of my model. So like it's a bit more than only what you wrote, but everything that you wrote here, I would agree with. So
amazing. So, thank you so much, Lukasz. Very, very elaborate answer. Love it. Any more questions to Lukasz? Now, while you have an expert in the session, make use of it.
Okay. You mentioned 2 types of nonlinearity, stress versus strain and geometry. Are there other types of nonlinearity, like material temperature? Are there types of simulation more complex? Okay. There are a lot of weird nonlinearities. I am a structural engineer, which means that for me, the stress-strain or material nonlinearity and the geometric nonlinearity would be dominant. Of course, I would say that there is, as you write, the temperature dependence of parameters. I even mentioned it briefly, right? In structural design, you usually do not produce a material that you hit a model and the yielding change. You just check what's the maximum temperature of the analysis, and you assume the material parameters for this temperature from the get-go, essentially. But of course, you could do a more complex nonlinear material model that would change the behavior of the model as the temperature of the model increased. So you have like the nonlinear material behavior in temperature 0, then in temperature plus 20, plus 40, plus 100, plus 200, whatever. And as you increase the temperature of your model and maybe some other loads, the material not only start to behave nonlinear because of stress strain, but also the increase of temperature changes how the material behaves. Still, I would say that that's a material nonlinearity. I wouldn't categorize it as something different. But there is one thing that can be different, and that is contact. I didn't mention contact today mostly because I hate semantic discussions. And you could spend hours debating whether or not contact is linear or not linear and so on, and it's pointless. But truth be told, without a doubt, you can have a complex nonlinear contact definition. You know, things like I am hitting a brake, I have a contact causing friction that causes heat, that causes the brake to heat up. That's a super complex contact phenomenon. And I think that in those cases, the contact would deserve dimension. So I usually say that there are like 2.5 nonlinearities. It's material, geometry, and the half would be the contact. To me, as a structural engineer, the contact is simply this touches this, right? So it is nonlinear in a sense because you need to iterate something like that. But realistically speaking, it's a pretty simplistic thing. However, in those very complex mechanical problems, nonlinearity of contact is like its own thing. So in those complex cases, that would be like a standalone nonlinearity. Although between those three, I think you would cover a lot. Although, you know, it's like when you want to do a PhD, you will always divide any field into small categories, subcategories, and sub-subcategories, right? So whether you will interpret the temperature dependence as a separate entity in a non-linearity realm than material properties, it's up to you because it's a semantic battle in some sense. You can discuss semantics, but it doesn't change the nature of the field. To me, since that all of this would be the oh man, I'm missing a word. I would categorize the nonlinearities in 3 ways. So I would calculate the temperature dependent in. So that would be nonlinear material, nonlinear geometry, and half, let's say, for the contact. And to me personally, I could, every nonlinearity you would tell me that there is, and there is, I could say, yeah, but that's a nonlinear geometry, right? Like membrane effect. It doesn't cause buckling, it causes strengthening of the model, but I would still say it's nonlinear geometry, right? And then things of this nature. So I would say those 3 are the main, but there are subcategories clearly. Lukasz is running his next nonlinear FEA class. Oh yeah, I actually am running a nonlinear masterclass. So if you would like to learn how to practically do nonlinear FEA in design, definitely join it. Super fun. What is this geometric nonlinearity? Could you elaborate on that? Great presentation, by the way. Thanks. Oh, thank you, Wojciech. Yeah, nonlinear geometry is a silent killer of engineering because nobody expected that. I use Zoom for my because I have an office and we have employees meeting online sometimes when someone works from home. So I actually know that there is a whiteboard I can draw. And nonlinear geometry is super. It's so simple that it will hurt your head when you will finally get it. Imagine that you have a string and you put laundry on it, right? So there is a sweater. Okay. If you would treat this string as a beam, and you have like, you know, a super simple static schematic, right? There's a force in the middle. You would calculate the bending moment, and then you will divide it by cross-section modulus. Section modulus, this is the English one, right? Of the cross-section of the string, which is most likely like, you know, 3 millimeter diameter circle. The stress you would get would be like infinite number, basically. It can easily go in tens of thousands of megapascals. And yet, somehow, miraculously, We don't do titanium laundry strings, right? It's a normal nylon thing that can withstand maybe 3 megapascals of stress. So how is it that it didn't fail? And to imagine why it wouldn't fail, I will do an experiment that's very simple. Normally, you don't draw static schematics like this. You would instantly add a sliding support on one end to make it statically determined, right? That would be the approach civil engineering teaches instantly. So imagine a laundry string that looks like this. I have a wall with a hook, and then there is a table, and I have a string. The string is attached here, so that's a vertical support and a horizontal support, so this one, while the string only lies on a table, like it lies on a table, like nothing is attached, it just lies there, right? So that would be a vertical support, but no horizontal support, right? Imagine that you are putting a laundry here. You already know that what would happen, it would go like this to the ground, and the string would simply fall from the table, right? Why? Because this is not how it works. And this is not how it works on a very simple principle. For the laundry string to work, you have to have 2 supports that can transfer horizontal directions. This is why you use like relatively good bolts to the wall to attach a laundry string, because you are afraid that they will be pulled off from the wall by the weight of the laundry. Why? Because when you have 2 supports 5 meters away, the string that deforms actually gets longer than 5 meters. So it has to extend to deform downward. If you have a sliding support, the string will just go closer. It doesn't have to expand, and it will go down. But as it expands, if you block the horizontal deformation, you get 2 horizontal reaction forces and a tensile force in the string itself. And this tensile force times the deflection, and of course there is a second force in a pair as a tensile force in the support, you have a pair of forces with a certain distance, and this is how it works. Note that it has very little to do with stresses whatsoever, and it has everything to do with geometry. The model deformed, the string did only one thing, it bended downward. And this bending elongated the string. This elongation caused normal force in the string, tension, and this tension was the thing that made the string survive. This is why it would fall off from the table here, because there was nothing preventing this horizontal movement. So nonlinear geometry effects are those things that are heavily impacted by the fact that your structure deformed. And that's it. If your structure deforms very little, there is no nonlinear geometry effect at all. But if your structure deforms a lot, things start to happen to the structure. The structure itself, as deforming, can generate additional stresses. It can strengthen itself. It can weaken itself. It can run away from loads. And those kind of things are nonlinear geometry. So every stability failure would be a nonlinear geometry problem, and a tensile stress you can see here is a nonlinear geometry. But what I have to also add is that you don't really want to think that nonlinear geometry is good. It's neither good nor bad. Sure, the string gets it better because the stresses in string compared if the string was a rigid beam and a membrane state element, the stresses here would be like 1,000,000 times higher. But the supports in this schematic get a huge horizontal force they have to deal with. It's not for free. Something will get it better, something will get it worse. So it's not like, oh, I have a structure and I didn't use nonlinear geometry, so I'm on a safe side. This is not how it works. The nonlinear geometry is always there as your model deforms, and it will simply push the load to different random directions, make hooks in your structure and so on. And this is a dangerous thing to ignore. So yeah, like if I would have to explain what's a nonlinear geometry in like a few minutes, that I think that would be.
Nice.
Okay, so nonlinear analysis is more accurate because it takes into account the changes in parameters like elasticity and rigidity modulus, which we normally assume to be constant. Yes, and because of this, the computation time for a nonlinear problem will be much more than linear analysis. Kinda. Like, yes, you take into account the actual stress strain chart. So this clearly, like the linear analysis have a linear way, right? And a nonlinear analysis has the whatever nonlinear material model you define, you decide to define. So to this, I agree. Although the problem with computing time comes mostly with, imagine you have an equilibrium path of your model that looks like this, right? So, well, no, that's this I will draw it again because let's do like this and then this. It's not a problem of the shape, it will work the same, but it's way easier to draw it this way. Right? So if I would assume that it's a linear problem, I would follow this curve that is tangent to the beginning. And solver does it, right? So let's assume that I want to apply this load. Linear FEA would do this. Apply this load, calculate the deformation, check convergence. I'm fine, everything works. Ta-da, you have your outcome. It's a stupid outcome, completely not on the equilibrium path of the model, but it's an outcome you've got. Right? And a nonlinear FEA says, hey, wait a sec, that's a stupid outcome, right? Because it knows that I have, for instance, stress is higher than yield, and it reduced the stress, and then suddenly the model is not in equilibrium anymore, and so on and so forth, right? So we'll say, okay, I will go down here. This is not the load increment I wanted, so I will try to guess again, sometimes parallel to this, sometimes tangent to that. It depends on how you set your Newton-Raphson iterations. And I will try again. Again, I will fail. Again, I will try. I will fail and try, fail and try, fail and try. And finally, I will succeed. Each of those steps takes as much as a linear analysis. So, and this is only a single load increment. And usually you will apply load increments in, you will apply your load in several increments. So clearly this will be a problematic thing because not only you get iterations that last as long as linear analysis, but you have many increments and each have many iterations. So this all multiplies the time a lot. And this is why computing. Mesh convergence for nonlinear analysis, which is the best way to determine the minimum mesh size when you use explicit solver. Whoa, man, Romano, first of all, I'm not using explicit solver because I don't have to. I don't deal with crashes and so on. So please bear in mind. However, what I would suggest is that you read about mass scaling for one, and then the velocity of an impact wave. If I recall, that's like 5,500 meters per second in a steel. And then what's important is the time needed for the wave to go through an element, right? And then the smaller the elements you get, the shorter the time. So your explicit time step will be so small that it will never compute, basically, or at least if you don't have like a super fancy machine. And when it comes to mesh convergence, you always do it the same way. You just make it coarse mesh, calculated, smaller mesh, calculated, smaller mesh, calculated, and compare outcomes. If the outcomes are similar, at some point, like, of course, like, so imagine that you have a mesh size and like this is like a lot of elements, and this is the outcome, whatever you measure, like stress in a place of interest, deformation in a place of interest, something like this, right? Then you have few elements, that's the outcome, more elements, usually the stresses are higher, this is why I'm drawing this upward, not downward. Then you have more elements, more elements, more elements, right? And you get it. And it will go like to, it will, like, I don't know the English word for it, like it will go close to a horizontal line.
Asymptotically.
Yeah, okay, like I had to, like, I wasn't sure if that because it's similar to Poisson, I was not sure. So the trick here to make it easier on you would be to, instead of using n, to use 1 over n, because then you have a chart when this is few elements, this is more elements because I'm dividing more, this is more, this is more, this is more, this is more. And it's actually easier to say when you are crossing 0, which would be the infinite amount of elements, and that would be the correct answer. Although, like, do you really want to like execute your nonlinear FEA analysis 24 times to get it? That's tricky. Like, it comes with experience, I guess. You also notice that like plastic strength do not change that much, and buckling capacity definitely, after a certain threshold of elements, buckling capacity remains the same. So if you have a buckling wave like this, if you have like, I don't know, 6 elements here on the wave, then it's most likely sufficient. If you're like super pessimistic, you can have 10 elements per buckling wave, and like having more doesn't increase the accuracy at all. So you kind of like, as you go and you do it more and more years, you kind of just know by looking at the model if it's meshed or right or not. But doing the actual mesh convergence, like the scientific study, would take insane amount of computing power. But like practically speaking, this is what you should do. You can, of course, do the convergence check on a linear model and then use the mesh that converge on linear analysis in nonlinear analysis, although this approach is problematic, at least because you have stress concentration. Hope we can cover this one quickly. Romano, last question before we switch sessions. Okay, so yeah, sorry, Joseph, like if you would say it, I would try to be briefer.
All good, Lukasz, I know you have always great answers, because we wrap it up now because Guillaume was waiting in the next session and doing some nonlinear FEA with Calculix.
So you know, I'm super proud that I've managed to say everything I wanted to say, and I'm also extremely sorry that I was late. Sorry, I promise that it won't happen.
It was worth the waiting, I'm sure.
Thanks, guys. So I hope that you enjoyed. Have a wonderful time, and see you around.
Bye-bye.